Today it's our great pleasure to welcome Professor Toscani from the University of Pavia for this 8th Lumer Lecture. And so we're very happy to welcome you for this lecture. And he will be talking about social phenomena from the viewpoint of kinetic theory. Thank you, Jeff.
Okay. What I say, I'm very happy to present this argument, and I hope I will catch someone of you towards this new application of kinetic theory. So maybe it's not so new, since I think I've been interested in this topic at least in the last 15 years. But any year there are new applications of this matter, and so I think that it could be really interesting to give you the flavor of what myself and the people that work with me are doing. I will be as elementary as I can, and I will present almost all true examples. And I hope that this will be simple also to understand for you that work with me are doing. I will be as elementary as there is some return of my voice.
Yes, I think someone had his mic on, but then it's off.
Okay. So in any case, I will split my talk into parts. In the first part, I will present you the idea which is behind this modeling of socioeconomic phenomena. And in few pages, in few slides, I will present the ideas which are taken from classical kinetic theory of rarefied gases. And then I will start with some example, really elementary, but I think interesting from the historical point of view. In a sense that you will immediately understand that the socioeconomic modeling started many years ago, more than 1 century ago, even if it is not so well known. And then, in the second part, I will move to a particular example that was the first example in which I discovered this application of log normal distribution, and is really important application in human behavior. So this is part of a lot of work. Here I give you the name of the people that are presently working with me, and we will work on this on two aspects. The first aspect that I will present today is the mathematical modeling, and more or less everything will end up with equations of Fokker-Planck type. And the second one is related to theoretical aspect, since this new type of Fokker-Planck equation requires the knowledge of differential inequalities that were never been touched before. And this has a lot of interesting theoretical aspects that I will not treat in this talk, but then you can go to my webpage and to check in various papers the idea which are behind. But let me start with a page of a paper that I wrote with a lot of co-workers in 2004, let's say more or less 20 years ago. And this is the introduction of a paper about entropy and entropy type inequalities. And it says that in many novel applications, the modeling involves the knowledge of the behavior of systems composed of a large number of interacting particles. One of the main features of such system is their tendency, if left alone, to converge to an equilibrium configuration as time becomes large. Usually this time is rather small viewed at our macroscopic scale. This is even part of our daily experience at the macroscopic scale. Whenever we create a breeze in a room by opening a window, after shunting it again, the gas will come to rest in a very short time. Very often, there is a thermodynamical principle underlying this property of trend to equilibrium. As time progresses, interaction between particles lead to the increase of a distinguished functional called entropy. The Boltzmann equation is the most famous kinetic model, both due to its important current applications and for its historical reasons. For this model, Boltzmann proved he celebrated his theorem about the increase of the entropy, which was the first analytical proof ever of the second principle of thermodynamics. So everything starts with the Boltzmann equation. And what is funny is that the Boltzmann, when I started with this job, the spatially homogeneous Boltzmann equation was not so well studied, since people were interested in finding existence theorem for the full Boltzmann equation, in which particles not only relax toward equilibrium, but they move and they are transported in view of their velocities. But if I consider the spatially homogeneous Boltzmann equation, in which the variation of the distribution density is related, is modified by collisions only, then the collisional integral, this Q of FF, is some sort of, let's say, difficult integrals in which it appears the binary collision between particles, and V plus W, omega, W minus V omega, V minus W, W minus V omega are the velocities after the collision, while V and W are the velocities before the collision, and beta is the frequency interaction kernel, which usually is considered for our potential, which is written below. Let's say it's not important to look at the spatial form of this collision integral. Simply it says it measures the variation of the density due to interaction between binary interaction between particles. And this is the structure that Boltzmann gave to the equation. So particles collide, they collide in an elastic way, they conserve momentum and energy. And if you introduce the so-called Boltzmann H functional, which is given by the integral of the density times the logarithm of the density, then it's easy to evaluate the variation in time of the density. And the variation in time of the density is written in terms of these collision integrals multiplied by log f that can be written in a way in which you obtain that this derivative of the H functional is known as a sign, and this sign is negative, in the sense that you produce you have some sort of entropy production. Yeah? What means that if you have a solution of the Boltzmann equation and you evaluate the derivative in time of this Boltzmann H functional, you find that there is a sign, and this sign is less or equal than 0. And if you check when this entropy production is equal to 0, let's say when Q of FF is equal to 0, you discover that there is a class of function that satisfies this equality, the so-called Maxwellian. And if you normalize, considering that mass, momentum, and energy are preserved by the elastic collisions, then you obtain that the entropy as a sign decays, and it decays unless you are in a steady state, which is written in terms of the velocity, like an exponential function, which is written here. The Maxwellian is a normal density in dimension 3. This is a very deep result. So there is no way, when you have a huge number of interactions, the interactions are such that you move always in a arrow of time, such that there is the entropy which has a sign, and the H functional is usually considered minus the entropy. So the entropy increases, and when it reaches the maximum, you are in equilibrium, and you have the exact form of the equilibrium. Clearly, what is not written in the book of kinetic theory, that this equilibrium is a consequence of the type of collision that you have. If, for example, you consider a collision which is not elastic, then you don't realize that there is no equilibrium of this form. This equilibrium is a Dirac delta concentrated in a point. The same you can do if you are in a background, considering particles that are colliding with particles which are in equilibrium. This simply means that instead of considering the bilinear Boltzmann equation, which is a nonlinear equation, you consider a linear equation in which the derivative of the density is driven by the collision of the particles with the particles of the background, and the background has particles in equilibrium. Both equations have a similar effect. The solution converges toward the steady state, the Boltzmann theorem holds, and equilibrium is reached in consequence of few properties. The first property is that you have repeated elementary interactions. You have the boundedness of some moment of the density. In the case of the Boltzmann equation, you still have equality in time of the energy in the case of the dilute gas. And then you have the validity of, let's say, of an entropy theorem or of an H theorem. So this is the picture. And then clearly, this is the picture that you have when you have particles of a gas that are of a dilute gas that are colliding in a binary way or in a linear way. And then if you change the picture, you have a different equilibrium. So for example, the first application outside the classical case of dilute gases, which has been made by kinetic theory, using collisional type equations, is the natural setting in which you have studied the distribution of wealth in a society. And so here you simply change the name of what you are studying. Instead of an ideal gas, you have a market. Instead of molecules, you have agents. Instead of collisions, you have trading. And instead of an elastic, you have a money preserving collision between two molecules. And the idea which is behind, which is more or less what has been done with the econophysics society, is that a trading market, which is composed of a huge number of agents, can be described using the law of statistical mechanics, and so using some sort of Boltzmann type equation. And instead of having, in this case, relaxation toward the Maxwellian equilibrium, you have a relaxation towards a different equilibrium, which is determined by the law that you fix in the trading event. This is related to the nonlinear part. Clearly, you can consider also interaction with the background, and in this case, you have a linear model. And in linear model, you fix a certain trait of the agents that can be the wealth, it can be the opinion, it can be the knowledge, or whatever you want. Then you consider interactions, and then the interactions modify the density function. And if you write the equation for the variation of the observable quantities, here clearly I always use the weak formulation of the equation, then what happens? The variation in time of the observable evaluated along the solution f of xt is simply given by a sort of frequency which is similar to what you have in the Boltzmann equation, and then you have the difference between the observable in the new variable which is modified by collisions minus the function in the original variable, simply weighted by f of xt. And so what you have is a complete picture that says, so for example, if phi of x is equal to x, you are evaluating the first moment. If phi of x is equal to x squared, you are evaluating the second moment. If phi of x is equal to 1, then you are evaluating the variation of the mass. And what you expect is that since you have repeated microscopic interaction, you will converge towards an equilibrium. And the equilibrium that you find is deeply related to the microscopic interaction. So give to me the microscopic interaction, and I will produce the mechanism that gives you what you see let's say, like a steady state, like a probability distribution in general. This more or less is, I start from the original picture of the Boltzmann equation. I move to some other relaxation problem, and I use more or less the ideas from kinetic theory to build up what I want. There is an interesting example. Let's say, really, this is really interesting, since it's something that is known, is very well known. If you go on the web, then you find also the reproduction of what happens in this Galton board. Is an experiment obtained by Sir Francis Galton in his book in 1889, and it was motivated by a social problem, in the sense that Galton was studying what happens to a population in which people can have repeated choices, and the idea is that there is a natural inheritance. So you start from zero, and then you fall, most of people does not fall far away from the 0 point. So this is not pleasant, by the way, but it's reasonable. And the way in which we was able to produce this result, he invented a device in which balls subject to gravity then exhibit repeated collision before falling on the ground. And repeated collision in which you have a symmetry. And at the bottom, if the number of balls is sufficiently high, you can see that you have a profile of a Gaussian density. So you have a profile of, let's say, of the same thing that happens in the Boltzmann equation. So this is simply a Gaussian in dimension 1. This is the original picture in the book of Galton, and in which you have pins and then balls that go down. And this is what you see in a more, let's say, much more modern picture. You have balls that start from above, then they have triangles, and then at each triangle you can go on the right or on the left. And then you see at the bottom there is this profile in which most of the balls are very close to the original line in which the ball enters into the game. So how to treat this problem from the mathematical point of view? Let's say Galton experiment is equivalent to a Bernoulli trial. Let's say you start and then you choose, you have two possible outcomes, like tossing a coin. You have success and failure. The probability of success is 1/2, and it is the same every time the experiment is conducted. And when I was teaching, now I am retired from 3 years, when I was teaching to my students, I was saying that it's like tossing a coin many times, and then you can reproduce the mechanism instead of moving on the entire, only on +1, +(-1), +2, -2, and so on. You can reproduce this experiment moving in the half plane. So to give a continuous description of Galton experiment, you have a probability density. This probability density changes in time at each step. The probability is changing the same, that is 1/2 of the probability to go to the right at time t plus 1/2 of the probability to go to the left, in the sense that if in a certain point x, you are there at the time t plus delta t, you are arrived with probability 1/2 from above on the left and from probability 1/2 from the above on the right. And then if you expand in Taylor series this expression, and you take the classical diffusion limit, delta x to the square over delta t, and you suppose that this limit is finite and is bounded away from 0, then immediately you realize that your probability satisfies the diffusion equation, so the heat equation, in which the diffusion coefficient is 1/2 of sigma. And this is very elementary. And then you observe that you start from x equals 0. And so you start from from a certain amount of heat, which is concentrated in x equals 0. And what happens if you start from a source of heat which is concentrated in equals to 0? Then you obtain a source type solution. And the source type solution of the heat equation, or the fundamental solution, is a Gaussian density which depends on time, and that is written below. And so if instead of using the Galton board, you use the same mechanism on the full plane, half plane, then you realize that what you obtain is exactly a Gaussian density, which is time dependent. So this is the classical way that you find on books. And then let us do the same experiment by using this idea of kinetic theory. In this case, we have no one Galton board with many balls that are falling down, but I have a huge number of Galton boards, each one with a ball. And then I perform experiments simultaneously. And then at a certain time t, I denote with f of xt in dx the percentage of balls which at that time lie in the interval x plus delta x plus dx. In this case, I have really a simple elementary interaction. Let's say if I am in a point x, after an interaction, I go in the point x plus eta, where eta is a symmetric random variable that takes value plus or minus capital L over 2, where L is the length of the bases of the triangle, with probability 1/2. Clearly, the mean value of this random variable is 0. The variance is L2 over 4, and I call this variance sigma. And if I take, in this case, is something, so is a linear Boltzmann equation that I am reproducing. Since any particle is colliding with the background, and the background is exactly this device, if the interaction kernel is constant, the kinetic equation, which is behind, simply says that the variation in time of f of xt is equal to the mean value of the integral of phi of x star minus phi of x in terms of f of xt. And consider that initially balls are concentrated in x equals 0. This is a very simple equation. And then I check the main observable that I can obtain from this equation. If I take var phi of x equal 1, then immediately, if you go back, phi of x star minus phi of x, if phi is equal to 1, is 1 minus 1, so it's 0. So the mass is preserved in time. And so if I start with the probability density, then I remain with the probability density for all subsequent time. And I simply get conservation if I take the observable equal to x, since the mean of x star minus x is equal to the mean of theta, and this is equal to 0. And so the mean is preserved. Unlikely, if I take the variance and I evaluate x star squared minus x squared, and the computation is simple, this is equal to sigma. What means if I take the variation of the second moment, this is equal to sigma time the integral of f, which is equal for all time, this is the mass, is equal to 1, and so I get sigma. But if the variation of a certain function is constant, and consider what happens when time goes to infinity, this means that the variance diverges with time. This is a diffusion process, so it's natural that the variance is diffusion with time. How can I check what happens precisely in time? The idea is to shrink the domain. Instead of considering the collision or the interaction, x star equal x plus eta, I consider an interaction in which I short the basis of the triangle of a fixed quantity, which is lambda less than 1. So I consider as new interaction x star equal x times 1 minus lambda plus eta. Clearly, if I shrink the domain, I do not modify the shape of the density. And as before, the mean value remains equal to 0. But when I evaluate the variance, the variance is now it depends on the value of x. And if I substitute this relationship inside and evaluate the derivative with respect to time of x squared, then I get that is equal to what I had before, let's say sigma times the integral over f, minus a quantity which is related to lambda times the same second moment. And if you solve this differential equation, which is clearly a first order differential equation in the second moment, you realize that the second moment remains uniformly bounded in time. I give here the solution of the differential equation. Let's say at the time t, the second moment depends on the initial value times an exponential, and since lambda is bigger than 0, it disappears when time goes to infinity. And then there is a second time, which depends on, let's say, on the quotient between sigma and lambda, let's say on the quotient between the variance of the random part and lambda, which is the shrinking of the times a function which converges to 1. Now, like it happens when you reproduce in the half plane in a continuous way and you arrive at the diffusion equation, you can reduce the size of the triangles in Galton experiment, then you reduce the shrinking parameter and the time in such a way to still observe this decay of the second moment towards a value bounded away from 0. And to do this, you have to do, in other words, the same scaling of the diffusion approximation. Let's say sigma, it goes like the square of the random part. Lambda, it gives, is what is the shrinking of the domain. So here you have sigma over lambda that has to be fixed. And so the scaling has to be chosen in such a way that sigma is, it goes into epsilon sigma, lambda, it goes into epsilon lambda, and t, it goes in over t over epsilon. In other words, what you are doing simply the fact that each interaction produces only a small variation, and to see the effect, you have to wait enough time. This is the basis of all the reasoning. You write a kinetic equation, and to extract information, you try to extract information, reducing the process, considering the so-called grazing collision, which is a procedure which is well known for the Boltzmann equation. And grazing collision are the interaction, the collision which does not modify in a sensible way the velocity after the collision. And what you get? Well, simply, you take a regular observable function phi of x, and then you expand in Taylor series, and you can do this since you are doing a small variation. This in the mean, this variation is equal to epsilon, which is written in red, times something which is inside, plus a reminder. Here the reminder is not written, but there is a reminder that disappears when epsilon goes to 0. And what you get if you scale time is that the variation of this observable is driven by that function written in red times f of xt, which is nothing that the weak form of a Fokker-Planck equation with constant coefficients. And so in the grazing limit, what you get from the Galton board is that the solution, once the domain has been shrinked, is given by the solution of a Fokker-Planck equation, for which there is an H theorem behind, and for which there is a steady state, which is a Gaussian probability density, which depends on the shrinking parameter and on the variance in such a way that you write this. And so you can do the same approach, but using a different, let's say, a different idea. So you write an elementary collision, you write a linear Boltzmann equation, Boltzmann type equation that obeys, is driven by this elementary collision. You shrink the domain in such a way to have a bounded second moment, and then you obtain in the grazing limit a Fokker-Planck equation for which you can explicitly found the steady state solution. And this is not a fundamental solution which is expanding in time. This is exactly a solution that, so it's exactly in the spirit of the Boltzmann equation. And this is something that you can do simply by this modified Galton experiment. To see if you run once, then you get some, and then you run 5, you run 10, and when you write 200 runs, you have a perfect Gaussian die. And here the collision is exactly the modified collision in which I took the shrinking parameter. Nice. So this is the old experiment, but the subsequent step is to do a similar experiment, not with a symmetric interaction, but with an asymmetric microscopic interaction. And the result is that you obtain a skewed distribution. And if you use the good interaction, elementary interaction, then you obtain in the bottom a log normal distribution. Why I insist on log normal distribution? For the simple reason that historically, just after the Galton, the Galton book about natural inheritance, there was an experiment constructed by Kapteyn in this book, Skew Frequency Curves and Biology and Statistics. That is exactly at the, let's say, 120 years ago, in which he produced a board able to distribute balls according to the log normal distribution. And let me explain, since this experiment is really interesting. Look, everything, or people who knows that the log normal distribution is obtaining when you have an elementary interaction, which is given by when you have a certain value, then the next value, let's say the interaction is 1 plus a random contribution, and always in this way. When you have x0 is equal to 1, the second one is 1 plus this square root of sigma eta, the second one is 1 plus square root of sigma eta, eta 1 times 1 plus sigma eta, eta 2. And so you have a product of a certain number of independent variables, not the sum, the product. And this is the elementary interaction. This is the elementary interaction. And you can obtain some sort of Galton board simply passing to the logarithm. If you define epsilon equal to the logarithm of x, then epsilon star, using the property of the logarithm, satisfies epsilon star equal epsilon plus the logarithm of a certain random variable. The difference is that in Galton experiment, one had a random variable, a symmetric random variable. Here you have a random variable which is no more symmetric. And then you perform the same computation. And as before, what happens if you shrink the domain? So let us shrink the domain. I take this collision for the logarithm. I shrink the domain. Epsilon star is equal to epsilon times 1 minus lambda plus the random part. And I go back after the shrinking. Simply means that the shrinked collision is x star is equal to e to the power 1 minus lambda multiplied by the random variable 1 plus square root of sigma eta. And then you can rewrite this like e star is equal to the previous one minus a function multiplied by x plus another function multiplied by the random variable eta. So in other words, you have a law like the Galton law. I go back one moment, like this one, in which you have x star equal x plus eta, in which here you have the coefficient of x is minus lambda, the coefficient of eta is equal to 1. In this case, I have a much more, let's say, involved relationship in in which you say that more or less you have x star equal x minus a function which multiplies x minus another function which multiplies eta. And if instead of lambda, like before, you use epsilon lambda, and instead of sigma, you use epsilon sigma, so you use the same scaling, then you realize when epsilon goes to 0 that the coefficient, the epsilon goes to lambda log x, and the coefficient of psi goes to the square root of sigma. And then you perform the same Taylor expansion, and you conclude with the fact that in this case you arrive to a Fokker-Planck equation in which you have no more a constant diffusion, but a diffusion that depends, is proportional to the square of the variable x, and you have a drift term, which is no more a classical drift, but is a drift in which you have x log of x. And this is a Fokker-Planck equation with variable coefficient of diffusion, which are some sort of nonlinear function determining the drift. And if you do computation, you see that the steady state is exactly a log normal density. And so the two examples, Galton examples, a Kapstein board, one gives you the Fokker-Planck equation with constant coefficient. And here, I have a Fokker-Planck equation with non-constant diffusion and drift coefficient. And so, and this is the Kapstein idea. And if you do, like before, you use not exactly the limit Fokker-Planck equation, but you are doing the job with this shrinked domain with the Kapstein experiment, that you see at the end, after 200 runs, you have exactly the picture of the log normal distribution. So the moral is that the original experiments of Galton and Kapstein clarified that most probability density can be obtained by repeated trials, and at each step, the elementary interaction is determined by the sum of two contributions. One is deterministic and one random, and the joining of the two parts ultimately determine the shape of the self-similar of the steady profile. And so, in general, if you want to reproduce some sort of social phenomena, and in many practical situations, the social phenomenon is determined by some sort of asymmetric behavior, then you consider an interaction of the type in which you have the value x, and then you modify the value x by a certain function phi of x multiplied by x, and then you have a random part, which is lambda of x multiplied by eta. And the two functions that you introduce, which are obtained looking at the modeling assumptions, then determine the shape of the equilibrium configuration. So hopefully you understand what is the idea behind the mathematical modeling of this type of phenomena. And this is a picture. This is the point in which I started to be interested in log normal distribution. A few years ago, a colleague of mine arrived into my study and said, "Do you have some idea of how can we treat this problem?" These all lines are the services made by people working in a call center. Each color is represented the length of the service, and there were 180 people working there. Each people had a certain number of works, and then they wanted to understand people what was let's say organizing the call center was interested in capturing the distributions of the call center service time to understand more or less if the variance was small or someone was outside of the variance, so it was not working so well, and so on. And looking at this is simply a line of one man in one day, and there were 180 of these lines, and they're multiplied by 180 days. And then how to extract information from this? And then I said, oh, maybe if you want to extract information from this, like it happens in Captain Experiment, you have to look at data in a logarithmic scale. And remember that in logarithmic scale, you see much more. This is what is the learning that you extract from Captain Experiment. And in logarithmic scale, what you see is that you obtain some sort of Gaussian symmetric lines distribution. This is the logarithm of service time. And so the idea is that when people is working, the service time obeys some sort of asymmetric law that produces the log normal distribution, or something which is very close to the log normal distribution. And we started to think at the way in which we can produce this behavior. And this is the idea. So agents that work in this call center have precise instructions from the service manager. Each service has to be done in a certain ideal time, which is called W bar. And this, of course, is not obvious that you can do this in this ideal time. You can use more time, and in any case, you have to fix some limit time for the service. And this limit time is denoted by this WL with the bar. And it is typical of people saying, but if I can do this in 5 minutes, but in principle, they say that I can do in 10, then I can do in 10. So it's easier. And so most people will take this new value instead of the ideal one as the significant time to respect. And then I do the same that I did before with Galton board. And let's say that if I did a service in a certain time W, then in the new service time, I will use a modification, which is given in terms of this W of W over WL, plus a certain random part, which depends on many factors, but clearly it can be that there is some randomness in this behavior. And as before, I take the variable theta in such a way that the mean is 0 and the variance is equal to sigma. This function C plays the role of the value function, which is an idea that goes back to Kahneman and Tversky in their famous paper on econometrica. Let's say it describes the way in which people is looking at a certain phenomenon. I will be more precise above. In the idea of Kahneman and Tversky, the value function is a bounded and concave function, which is positive above the reference value and negative below. And it's immediate to conclude that the function which is with this characteristic is the function mu times s to the power delta minus 1 over s to power delta plus 1 with s bigger or equal than 0. I will not insist on why this is the function that you use, but the fact is that the idea is that you cannot move a service from a certain point to the next one, changing completely the time that you are doing. And so you have to fix a certain bound from below and above. So if you can do something in 10 minutes, then you can do this in 9 minutes or in 11 minutes. And so this requires the presence of a certain denominator in the fraction that is such that you have this bound from below and above. This is the picture of this value function that is written there. You see, if you look on the x-axis, and then you have the the reference point, which is 1, and then you move on the left of minus delta S and on the right of minus delta S. When you go on the epsilon axis, did you see you have still a shorter interval above and a longer interval below. That expresses the fact that the sign, since that when we were able to do something in a time less than the limit time, then you will naturally tend to increase the working time. When you are above, you will naturally tend to decrease it, but it's much more difficult to go back and so to decrease the time than to increase. So, in other words, to arrive to the optimal service time is much more difficult if you have to short your time, but it's much easier if you have to increase the time. Yeah? I will do a different example of this fact if I have time. In other words, and this is the connection with prospect theory, the prospect an agent will have of his work will be completely different depending on the sign of the value function. If you are above, then you have to shorten your time, and so you have to work much more. If you are below, you can relax. So the situation is completely different. And then you can have other choices. You can use a different denominator, you can use a different numerator, but the important fact is that this value function has this interesting property that if you reverse and you consider the inverse of the service time and you do the computation with this value function, you see that also the inverse time leads to a value function which is similar to the value function that I gave before, except that it changes the amount that you can change, and it changes the denominator. And this is a typical property of the log normal distribution. If you have something which is log normal, then the inverse is still a log normal random variable. In other words, the asymmetry of this value function is very suitable to characterize phenomena that are described by log normal profile. And then you write, as before, the linear Boltzmann equation, which you insert this value function, and then you do the grazing-Linig collision, and you arrive to the Fokker-Planck equation I presented before in the Kapstein, which is given by this Fokker-Planck equation, in which you have a diffusion which depends on the square of the variable, and which you have a drift which is given in terms of W logarithm of W over WL. The parameter which appear are the parameters which are linked to the elementary interaction, and then you can conclude, you evaluate you solve the steady state distribution is given in terms of a log normal distribution, which depends on a certain number of parameters which are related to the service time. And here, so there are simply considerations of. And in logarithmic scale, what you obtain is very similar to what you obtained in the logarithmic scale of the data that you had. Sorry. Okay. How can I? Sorry for this happens. This is a classical mistake. I didn't touch my phone. And what you see, no, I have to, sorry. No, it doesn't work like before. How can I will be back. I think that now it works. Huh? As you see here, you have different type of service, and the log normal distribution that reproduce the services, clearly the number are not so high of data, and so there are differences, of course, but the log normal distribution follows very well the phenomenon. And now to end up, what I can say that this is something that explain a lot of interesting social phenomena. So, for example, body weight. If you go on the web and you look for data about distribution of the body weight in populations of, let's say, Western countries, then you see that body weights tend to follow a log normal distribution. There are a certain number of papers that are wrote here. And the appearance of this log normal distribution can be fully justified on the basis of the previous kinetic model. And here, don't read the whole slide, but the fact is that each one knows that there is an ideal weight, but to reach this weight is a completely asymmetric phenomenon. If you are below, you have the pleasure of it to reach this bound. If you are above, you have to stop to it, and this is completely different. And this is a completely, let's say, asymmetric phenomenon that can be described using the value function that I wrote before, and this leads immediately to a log normal distribution for the distribution of the weight. Maybe is the most, let's say, understandable example about why log normal distribution is able to reproduce a phenomenon of this type. A second one, which is not so well known, is the remark made by this researcher Preston in a paper in '81. He discovered that the log normal fit was fairly good for women in the United Kingdom in 1973, and this is the same. The age of first marriage is an asymmetric balance between the desire of using time to reach independence and the existence of a natural age bound to respect, which is related to motherhood. And Stefano Gualandi, which is one of my co-workers, went to the municipality of Milan. He got data of the last 20 years, and he tried to understand if this was this log normal distribution was correct or not. And here are the results. You see, the empirical theoretical distribution is almost perfect, except in one part, you see here, in which there is this you overcross, and this is around the age of 70 years, since there are a certain number of women which are married in the second half of their life. This is the difference. So this has nothing to do with motherhood, clearly. For the rest, it is approximately very, very good. Drivers in traffic. It has been noticed that is given by a certain log normal distribution. And this is, there is some asymmetry which is present. You have an ideal safe distance that you have to maintain, and so you are relaxed when you are far, and you are not relaxed when you are too close. And in this case, we are not using the classical asymmetry, it's a reversed asymmetry, but the value function for the inverse is of the same type, like I said. And so also in this case, you obtain a log normal distribution. Consumption. Here, the asymmetry can be simply saying, comes out from the fact that the human tendency, clearly, one prefers to spend than to earn by work. And last, maybe there are many other phenomena, but last I will insist on the distribution of cities of middle size. And in this case, log normal works well only exactly for the distribution of city of middle size. Since the last city of big size follow a fat-tailed, so a Pareto distribution. And so you have to match together here everything is written in log scale. So for example, these are the Italian cities in green, and there is a small part, which is the 6%, in which we use a fat-tailed distribution to obtain this picture. And this is this is exactly what you get. You have a perfect adaptation up to a certain point, up to 100,000 inhabitants, and then you have to, cities of bigger size have to be, are reproduced by a fat-tailed distribution of, so normal is red, and the second one, this part in green, simply follows the big cities, which are not, but the middle city of middle size. To end up, kinetic theory appears to be an excellent mathematical framework to describe the equilibrium distribution of a number of social phenomena, which are characterized by a certain asymmetry around an ideal value. And among others, log normal distribution is easy to fit, test, and modify, and hence is valuable to use to give answer to the formation of equilibrium social phenomena. And kinetic theory, I hope that you are convinced that I was able to convince you, is a powerful tool to highlight the physical reason behind the formation of these and other types of equilibria. And to end, there is a list of papers of the last years in which we studied a certain number of phenomena which are involved with social phenomena. And as you see, there are a list of applications, and what it retains is really interesting is that you can use this idea about value function in compartmental epidemiology. So for example, to study the evolution of the COVID-19, using the fact that this evolution, this diffusion is strongly related to the number of social contacts, and social contacts is a social phenomena. And so we thought to join classical models of compartmental epidemiology with social description of contacts. And so, for example, this is what we did together with Benoit Pertam and other co-workers in 2021, and from this many other papers followed, and I think that this is all. Thank you.
Thank you very much for this very nice talk. Are there any questions? There's a lot of clapping. Are there any questions?
I was too clear.
Don't see any questions for now. Maybe I can start. You talked at the very last about this fat-tail distribution. And is there a way to interpret it? So you showed us that the Gaussian distribution and log normal distribution can be interpreted in terms of this Galton experiment, where you have symmetry and then asymmetry. Is there a way to interpret it also from or not? So I'm not very familiar about that. So just...
I did not understand your last.
So I mean, is there a way
to? Is Galton and Kepler? See, simply, I think that is a good model to understand what is behind the kinetic interpretation. And then you asked what?
I'm just wondering if you can also obtain, so you obtain from the Galton experiment, you obtain the log normal. With asymmetry, you obtain the log normal distribution. And now, is there a way to obtain this fat-tail distribution? So this is even more asymmetry.
This is a nice question. So first, to obtain fat-tail in social phenomena is related to wealth, more or less, or to other phenomena like social climbing and formation of an elite. And so all phenomena in which you have a few people that take the power. With this 80-20, not from the Galton experiment, unlikely. I never thought to this, but it's an interesting question. If you start from Galton experiment is strictly related to the Gaussian, so to the normal distribution, and so the skewed phenomena that you can get from this is the sort of normal one. But fat-tailed distribution have no counterpart in the full of R. So it's something that they are related to the Barenblatt solution, to the fast diffusion case. So instead of having the Gaussian, you have the fast diffusion. But a fast diffusion is a nonlinear phenomenon, and you can obtain from a linear Boltzmann equation. So I think that in any case, it's a good question. I never thought to this. I will, having time, I will think. Yeah.
Thank you. Are there any other questions?
Can I maybe ask a small question?
Absolutely.
Also, the previous question was very good. How to get this power law, because there was statistical mechanics of money, and then I don't remember, but you somehow get these power laws as was the previous question. So this is an interesting question, really. And I have another question: is do you have some information theoretic approach to this, like you compute Kullback-Leibler divergence or something like that, like information flow?
I never touched this part, so I don't know what I can.
Yeah, I was just asking you.
No,
Mm-hmm.
I don't know information. I do not know.
So because I was just asking, it's okay. Just in case, because I think for log normal distribution you can compute somehow Kullback-Leibler divergence, and to see if how fast the system can go to this equilibrium distribution. I mean, this was just a question. Thank you.
No, what I can say is that if you have this Fokker-Planck equation that has a log normal equilibrium, this is easily related to the original Fokker-Planck equation by a transformation of variable. And so for the original Fokker-Planck equation, you have all theorems. So for example, logarithmic Sobolev inequality. And this result commutes into a result about convergence to the log normal distribution for this Fokker-Planck equation, but it's not what you are asking. So from the theoretical point of view, any Fokker-Planck equation which can be obtained by transformation of variables from the original Fokker-Planck equation has the same result, but it's not what you are asking. So I think you do it. Yeah.
Yes, but maybe if there is nobody else, maybe just one more question. The Fokker-Planck equation is gradient flow for the free energy, so you can,
absolutely. See, you can interpret in this way. I agree.
In this variational problem, so you can interpret this, yes?
Yeah, absolutely.
Yeah. So what would be the free energy then in your
This
example?
log normal. I never thought. I think that exactly you can obtain by this transformation of variable, but I didn't do the computations. This is a good question to ask to a co-worker of mine, let's say Giuseppe Toscani, which is one of which can certainly give the answer, but I think that no one touched this Fokker-Planck equation with this logarithmic drift.
Mm-hmm.
So it's new.
Thank you.
Thank you to you.
Are there any other questions among the participants? I don't know what's happening online on YouTube, but
I don't think there are any questions on YouTube. I don't see them.
Maybe I have another very naive question, because I'm not very familiar with that. But when you said at the very beginning the analogy with the market, then you say that the market was the analogous from in the kinetic theory, or well, in the theory of gases, of an ideal gas. And I'm not sure I understand how the analogy works. And is there any way of interpreting that analogy with another equation of state, or is it completely off? Or maybe it doesn't have anything to do with well.
This analogy is not mine, clearly. So this idea of treating a market like a gas goes back to let's say 28 years ago, when the world econophysics started. So this was an idea of Engel. Is a paper that is 40 years old. The analogy is simply that people trades, and usually the trade is a collision between two agents. They put money inside, and then the money goes outside with a certain risk. And the idea was to produce in this way a fat-tailed distribution, in which few people collect almost all the money of the society. And really we succeeded. So that there are many models in which you obtain this result. So the analogy, it works. Clearly the analogy works if you have a huge number of people that are trading. If 3 people are trading, no fat tail is produced. Clearly you need millions of people, millions of trades. Statistical mechanics requires many agents. But it's an analogy that works.
Thank you. So no other question? It was very clear. So thank you very, very much for your talk. Very interesting talk. Clapping again.
Thank you to you.
And thank you.